Hey, Dr. B here, and let's take a look at the difference between a chemical bond and an intermolecular force. As you might expect, a chemical bond are these solid lines here, whereas an intermolecular force is this dashed line right here. A chemical bond is within a substance. It's the solid line, and it's what forms the substance, a bond being the attractive force between atoms or ions. An intermolecular force is between substances, for which we use the dashed line. This is by definition intramolecular within the molecule. This is intermolecular for the intermolecular force between the substances. And you wouldn't be surprised to learn that the bonds are typically stronger than the intermolecular forces, although there is some overlap. And if you break this line, you break this bond, well, that's a chemical process. You are forming new substances. But if you break this dashed line, you are simply separating the molecules, and it's a physical change, typically a phase change. And if you hit the gaseous phase, well, you've overcome the intermolecular force entirely, and you have separate substances. Since we're talking about phase change often, let's have a good look at it. When you're in the gaseous phase, the atoms or substances are completely separate, and they're like three-dimensional billiard balls bouncing around. If they hit each other, it's simply an inelastic collision, and they keep rolling. Once you hit the liquid phase, the substances become much closer together. They experience attractive forces, but they are still free to move. They flow. Cool it down to the point where they become locked and you have solidified your substance. You have an ordered arrangement. The particles are now close together. The best they can do is perhaps vibrate around. That's a gas, a liquid, and a solid. You have either no intermolecular forces, some passing intermolecular forces, or locked intermolecular forces. All this is well and good, but most textbooks fail to point out that there's several classes of substances for which this model really fails, and I'm talking about anything for which you have a lattice. This could be a salt. Imagine sodium chloride, right? Sodium chloride does not consist of clean individual sodium chloride molecules. It's part of a complete lattice network. That means it's important to point out for ionic compounds, metallic compounds, and even network covalent substances, you don't have these dotted lines. You simply have a network where you have nothing but solid lines. Certainly they can still melt. You can have molten sodium chloride. You can have liquid metals. Perhaps even the network covalent compounds such as glass can be melted. Sure they can. But the forces are generally much larger. Not always, but oftentimes it requires much more energy since you have a complete lattice. That includes the metals, the salts, and the network covalent solids. This is an introduction to intermolecular forces.